Thank you. So today for the small presentation, I'll be presenting on using graph theory to gain insights about system models. I am Sophia Cordero. I'm a postdoctoral research fellow at ISAE-SUPAERO. So for the outline, thank you. We'll start with short background, OML and semantic patterns, system information, using as graph, and seeing the insights from them, and some conclusions. So for some short definitions, just to get everyone on the same page. So a network collection of objects in which some pairs of these objects are connected by links. Then we have what a DSM is. That is basically a map representation of a set of n elements, and is a network modeling tool, actually. Graph, that is a way of specifying relationships among collections of items that consist of a set of objects called nodes or vertices with certain pairs of these objects connected. So there has actually been in many domains, such as sociology and computer science, when giving any sort of information, in this case, networks or graphs, a recurring question, which is which of these nodes in the following slide, thank you. Yeah, so which of these nodes is more important? To answer this question, a whole plethora of centrality measures actually had been proposed to account for the importance of nodes of a network. So you have that centrality has been defined as the function or importance of a node in a graph. You can see basically you have concepts, you have relations, let's call them links if you want. So we can just ask ourselves, what is a system model if not a graph, if we take into account these concepts and relations. Next slide, please. So in order to construct an OML model, as previously in the morning Nicola explained, you need two main set of elements that are the vocabularies and the descriptions. And you have the available vocabularies online from the Integrated Model-Centric Engineering Team project that you can find as analysis, base, mission, project, and you can add to that bundle domain-specific vocabularies that you can create. So for instance, in the figure, you can see a subset of the ontologies that are used for probabilistic risk assessment that is available in that paper. The next slide, please. So the semantic patterns to be extracted actually from the system model and to be analyzed will depend on what sort of assessment needs to be done. So kind of going back to what Dave said is which questions need to be answered. There are many references for different sort of assessments. So there are two examples that I put in the slides for service security and obsolescence assessment. And for the sake of this presentation, I put a short example of an interface change assessment. So in the figure, you can find the subset of the mission vocabulary that is relevant from the context of the interface change assessment example. So you have components that present interfaces that are joined in conjunctions. So thanks to the OpenCSR tools, like previously mentioned before, like going from OML to OWL or OWLs to start Fuseki or OWL Sparkle, you can actually run queries on the OML system model, and you can extract the patterns that you need to study for the assessment, in this case for the interface change. So in this case, the concepts that you would query would be components, interfaces, and junctions, and the relations would be presents and joins. Normally, the results of the query, I don't know if it was mentioned previously, they can be obtained in CSV, JSON, and XMLs. So it gives you a lot of flexibility in how to analyze them. So you can do that with Python network libraries, for instance. The next slide, please. So as you can see, this is just an example of a public database of how it can be represented as a graph using actually Python libraries. And by treating the system model as a graph, there are actually some network metrics, as I mentioned before, and more precisely, the centrality metrics that we can use to see different insights. For instance, we have the degree that provides insights regarding the exposure within the network or the opportunity to influence directly. So for instance, we can identify a component that presents many interfaces. We have between essentiality, that is a measure of how much removing a node would actually cause the disruption of the relations between the other nodes. So for instance, if there's an interface change request, then a priori, thanks to the analysis, it is known that one of the interfaces that is changed would disrupt the system the most. So in some sort, to have a control or a monitor this interface during the design or during the operation, for instance. Then we have closeness centrality, which provides information about a point of rapid dissemination of information throughout the network. For example, an interface that if the interface fails, then it disrupts the data and perhaps whatever program or whatever initiative needs to receive the data. You have also eigenvector centrality. So this actually represents a node that might not have many connections, but the connections that is connected to actually have a lot of connections. So in this case, we could identify an interface of a component that has many other interfaces. So a point of, again, dissemination of information or a sort of interface. The next slide, please. So for the conclusions of this short presentation, we have, well, a big caveat that is that the analysis results are only as complete as the system model is, which brings us to the question, to have system models, it's normally a big investment. If somebody wants to try to model the whole system, as Dave said, you should try to model what you want an answer to. So there's also the case of it being a big investment to study historical data if you want to have inputs from previous programs to see which metrics work better. To do it in historical data can be tricky since the data might be incomplete or unavailable. And the funding would go to ongoing programs, for instance. So from the historical data, there could be some data correlations to be extracted to decide which characteristics are best for a certain architecture for a certain metric. As for the centrality metrics, we can see that they can capture how sort of important a node or a component is, or a certain concept within a network, which allows us to have a reasoning based on an objective criteria. And this leads us to the question of how many metrics exist that can actually be considered objective and not program dependent. And one of the conclusions is actually that the OpenCSR tooling makes the pipeline for the analysis quite straightforward. So there's no need to try to connect it to a query service and all of this. There are tools that are already make this possible. And I think the next slide, I put out the references for those who might be interested, and I think the slides will be available online, so you'll have access to that. So thanks a lot for listening, and I think I forgot to put my info, but you can find it online.